So today, oh, and then also before we get going, for anybody who needs a reminder, if you are registered in the seminar, to mark yourself as present in iClicker, which is open and available, so you should be able to do that. But I'm going to hand it right over to our presenter, Dr. Miguel Acevedo from the Wildlife Ecology and Conservation Department here at UF, and he is also a graduate of the Interdisciplinary Ecology program, and so he is here to talk to us about adventures in interdisciplinary ecology. Thank you very much for being here.
All right, I usually I usually walk around a lot when I'm giving a talk, but they told me that I have a very restricted home range today. So if I go out of my home range, could anybody tell me that I'm, me too, because I have a microphone. But anyway, thank you so much for being here. It's definitely an enormous honor and privilege to be here sharing some of my adventures in interdisciplinary ecology. Recently, I submitted my tenure and promotion packet. And there's some analogies between doing a PhD and submitting your TMP packet. First, it's a lot of work. Second, it's stressful. And third, it's a process of self-reflection. And in that process of self-reflection, I realized that I've had a very privileged and unique journey. And maybe I'll share it here with the SNRE folks with the hopes that there's a couple of lessons by the end of this next couple of minutes. So for those of you that don't know me, I'm a quantitative ecologist, which means that I do math and ecology, and I teach a couple of different courses undergrad. At the graduate level, I teach the quantitative analysis of animal populations, which is a class about statistics and estimating abundance and survival and all that. So if you're interested in that, come and see me, and I'll tell you when I'm going to teach it again. I also teach a class called The Professional Scientist, the other things we need to know, where we discuss things like leadership, time management, work-life balance, and all those other skills that complement our scientific skills. And I'm going to teach that one in the fall. So if you're interested, feel free to enroll. It's a pretty awesome and hopefully interesting class. In terms of research, I do a couple of different things. I'm interested in multiple things, but one of them, three things. One is I'm interested in populations that are disequilibrium with the environment, meaning that they're responding to climate change. I'm also interested in those that are recovering. So for example, sites that have been deforested, forest is coming back. So how are animals, recolonizing those sites that are being recovering? I'm also interested in diseases, particularly vector-borne diseases of lizards. I work with malaria in lizards. So yes, lizards get malaria. No, you will not get malaria from a lizard, but this stuff will not. Actually, I have a slide on it, but not too much about lizard malaria. And third, which is going to be the most of the stuff that I'm going to talk today, I'm very interested in collaborating with the quantitative folks, developing tools that can help us solve some of the most important problems in conservation and ecology. Before continuing, I like to make some definitions. So what I mean by interdisciplinary ecology versus multidisciplinary ecology. So when we talk about multidisciplinary ecology, let's say that I'm collaborating with a mathematician, right? So in a multidisciplinary setting, I do the ecology, the mathematician does the math, I write the ecology of the paper, the mathematician writes the math of the paper, we put it together and we submit it. It's sort of the sum of the parts. And nothing bad with that, that's pretty cool. I've done that, it's interesting, it's insightful. But when we're doing interdisciplinary ecology, there's something else. There's some magic that happens. There's some sort of something else. And that something else is the integration of the disciplines. Right? It's not everybody, working in isolation, but integration. The ecologist becomes a little bit of a mathematician. The mathematician becomes a little bit of an ecologist. And together, we create a product that hopefully will be way more than the sum of the parts. And that's what I'm going to be talking about that magic and that interaction that happens within the two. So how did I got interested in interdisciplinary ecology? So this was around 2005, just a little bit of back to the future. If you don't remember 2005, Facebook didn't exist in 2005. iPhones didn't exist. And this is important because I'm going to be talking a little bit about technology and all that. And none of that stuff existed. 2005. I was a first year master's student, very interested in birds and salsa dancing. This guy over there is my really good friend, Luis Villanueva, one of the most brightest, most capable collaborators I had in my life. And he was really interested in amphibians and computers. So, you know, we did different things. I did birds, and then Friday nights I went out and do some salsa dancing. Luis will do amphibians, and on Friday night he will get into his graduate student office and deal with boards and cables and all that. So one day, Luis, super smart guy, comes to my office and he said, Miguel, I got it. Sure. Congratulations, you got it. So what did you got? And he said, you know, and then he started telling me this story about frog loggers. How many of you have heard about frog loggers or ARUs or automated recording units? Right, back in the day, you know, there were no iPhones and all that. So there were cassette tapes, right? Cassette recorders. So there was these frog loggers will have a cassette and they will have a microcontroller that will press record every hour or so. And you have a couple of hours of recording that you can do automated in the field. In 2005, digital recorders started coming up and mini discs and all that new technology. And Luis was intrigued. He wanted to build something that will mimic that effect of the frog logger, that they can record automatically in the field. And we didn't have that technology, but he actually got it to work. He developed a microcontroller that you can plug into a digital recorder, and then we can record multiple days. So we don't have to, you only have to go to the field on a Monday, set up the recorders, go home, and then come back on Friday or Saturday, pick it up, and you have 5 or 6 days of sampling instead of just being there, you know, every day collecting the sample. So that was pretty cool. I was super interested in birds, so we got together and we said, hey, let's just see if this works. Humans versus machines. How many species can we get by recording and listening to them versus how many I can get just going to the field and doing my traditional point counts? Remember, point counts, they happen in the morning in one day. Transects for amphibians, they happen at night, one night. But these recorders can be there for 3, 4, 5 days. So we did that, and in this picture, actually, we published this in the Wildlife Society bulletin, and they asked us for a picture of us in the field, which was kind of interesting and kind of weird when you're talking about it almost multiple years after that. But anyway, that's us in the field. These are the recorders, and that's a microphone. So what we got was super interesting. So the machine, you can see this in 2 ways. Either the machine beat us, or the machine is pretty similar to us. Right, so the machine got some species that we didn't got, particularly because they were there a longer time. We also got some species that the machines didn't got because we have eyes and the machines don't. Right, we got some species that were detected by eyesight. But in general, it was a pretty good deal, right? The machines were there; they cost less than humans, right? Because if you take into account how much money does it cost to have a biologist in the field, that's a lot of money. So we were super excited about it, but we spent a lot of time listening to recordings and looking at the spectrograms. And then one day, this is Mitch A, my master's advisor, which by the way was also Orlando Acevedo's master advisor. And, you know, he looked at us, you know, always, you know, looking at spectrograms and listening to recordings and not working on our thesis, by the way. That was a side project. So he got a little bit worried and tense. And he looked at the spectrogram over here and he said, you know what? In his infinite wisdom, he said, if I can look at this and say, well, this is one species, this is a different species, this is one different species, I'm sure there's a program out there that can easily detect this automatically. There is a program out there that can easily detect this using software. And actually, he was into something. You know, in this case, evolution is actually on our side. Because think about amphibians, right? Amphibians, they don't have the colors of birds and all that. So most of the cues are auditory. So they have evolved to sort of limit the overlap in terms of acoustic space. So maybe that's a trait that, you know, we can use software to do it. So I looked for stuff. I look online to looking for this software, and I talk to people, and then I look online again, and I look online again. And the program that will easily identify species automatically obviously didn't exist. So that created a problem, right? I have an advisor that wants me to focus on my thesis. I have a problem that I wanted to solve. I wanted to detect these things automatically. So I went and did the unthinkable. I walk the 20 meters between the Department of Biology and the Twilight Zone, computer science department. And then we met. I talked to different people. Most people told me, I'm not interested. And that's an important lesson here, right? So when you talk to people, when you're trying to create these interdisciplinary collaborations, you approach people, not everybody's going to be interested. And that's completely fine, because if they're not interested, you don't want to work with that people. But out of 20, one will be crazy enough to follow you. And that's the person that you want on your team. And that crazy person, the first one, his name was Carlos Corrada. And we talked to him, we said, this is our problem, and we need some help solving this problem. And he said something that I will never forget. He said, that's a non-trivial, interesting problem. And, at the time, I thought, oh, that's an interesting phrase. But, in 15 years, now more than ever, I know there's a lot of stuff in this phrase. The first one is that's a non-trivial problem. Believe it or not, the mathematical problems that we ecologists have, they're pretty easy for these folks. They eat our math for breakfast. So whenever we are trying to gather, help from them, it's too easy there's nothing on them. There's nothing that they can publish on. So if you give them a problem that it's non-trivial, that means that it's win-win. That will solve your problem, but also have something for them. They're going to work on a problem that is going to create scholarship for them. And then the second part of this phrase is an interesting problem. Believe me, these guys are tired of doing image classification. These guys are tired of the same problems that they use in computer science. So if you say, we're going to save frogs, we're going to do conservation of frogs, they're like, oh, that's not a classic example that I see in my computer science book. So they're super interesting. So that's another lesson here, right? That we need to gather people that are crazy enough to work with us. Make it win-win, right? Something that they have something and you have something, and they have to be interested. Anyway, in the process, he actually called his brother, Hector Corrada. Hector, actually, interesting story there. He quit his PhD in classical guitar to study statistics. And he's doing AI and machine learning. And at that point, he was finishing his PhD in machine learning. Again, some of the smartest people I ever know. And he said, oh, sure, I'll help you out. So at that point, we deployed Luis recorders all through the island of Puerto Rico. We trained a fantastic group of undergrad researchers to train these systems, right? So they will listen to the recordings, identify the species, and create a big database that we can use to train the machine learning stuff. And we compare them. We compare 3 types of machine learning methods: linear discriminant analysis, decision trees, and support vector machine. Anybody here or in Zoomland working with AI or machine learning or any of that? Not here. But anyway, what I was going to ask is what's the most conspicuous lack in this slide is that there's no neural networks, right? What we're doing now in machine learning and AI is mostly neural networks, and we didn't try them. And that's because in 2007 or 8, when we tried this, neural networks were not really people say, they over-parameterize, they don't really work, let's just do super vector machines. And actually, things have changed today, right? Super vector machines that doesn't work, let's do neural networks. But anyway, so out of the 3 methods, then the support vector machines were the ones that work the best. And this is a game where you want to improve or increase the true positive, which is the probability that the species is accurately classified, and decrease the false positive, which is saying that this is one species and being wrong about it. All right. So in this game, if you look at it, the system worked pretty well. Most of the true positives were super high, and most of the false positive were below 3%. So we were actually pretty good. And more importantly, I was hooked. I was hooked because I already learned that if you have a problem and you cannot solve it, somebody else will solve it for you or with you. All right. So that's an important lesson, right? So now I have this idea that I can move away from, the ecology realm and look for answers. There's plenty of answers. There's plenty of tools there waiting for an application. So I started looking for, I want more classes. I want more of this. And I discovered there was this class called mathematical biology, which had the math component that I wanted and the biology thing that I was comfortable with. By the way, if you don't know mathematical biology, and I know it now, it's not really under 50% math, 50% bio. It's like 99% math and 1% bio. But anyway, I know it now. And I didn't have most of the prereqs. I took Calc 1 like, a couple of years before this, and that's about it. So, but we had some really good friends in the class. This is my friend Paco. There's a story about Paco. Remember his face, because at the end, I'm going to share a story about Paco. And this is another really good friend, Claudia Patricia, which I owe her a lot because she gave me a lot of tutoring. She gave me like a review of linear algebra. I never took linear algebra, a review of Calc 3, never took Calc 3, and all that stuff. So they were super helpful. And Professor Marcano was also super patient with my lack of math skills. But we studied different things. And one thing that we studied was reaction diffusion equations. Reaction diffusion equations are super cool because they describe some sort of change, a change in some substance. The examples that we studied in the class were the flow of things in the kidneys. But it's the flow of something, right? And they have two components, a reaction and a diffusion. The reaction means reproduction, how things reproduce. And the diffusion part is the spread. Think about this for a second. They describe how things reproduce and spread. How things reproduce and spread. Does that sound familiar to you? Doesn't that sound like pretty much anything in ecology, right? That things reproduce and things spread. So I was like, this is it. This is, I want to use this. This is like the, thing that I want to use. And when you're Puerto Rican, there are two ecological problems that you're super familiar with. One, it's hurricanes. And the other one is forest recovery. Believe it or not, the island of Puerto Rico, it's actually going in the opposite direction. The island of Puerto Rico, the forest is actually coming back. At the beginning of the 1900s, there was less than 10% of the forest cover, but that forest cover is coming back. And here in this figure, we have a picture of in the 1950s, there's around 17 or 18% forest cover, but look in the 1990s. Forest actually coming back, and today is around 60% or so, maybe a little bit more than that. We might be reaching that plateau, but the forest is coming back. The forest is reproducing and spreading. So I said, this is it. I'm going to apply reaction diffusion equations to describe this process of forest spread. So I had to do some tweaks. I simplified the problem a lot by just taking a rectangle and not this physiography of the island of Puerto Rico. And then I applied this model that looks like a lot of like ants on the screen, but it's qualitatively, it's pretty simple. It's the change in forest cover over here. This is the reaction or how it reproduces, and this is the diffusion part. For the reaction, we just assume a logistic growth model. So forest cover increases, and then when it reaches 100% in that pixel, it ends. And the diffusion is a simple diffusion in 2 dimensions. So you can imagine a drop in a surface, and that's pretty much what we're doing, right? It's a drop in a surface. And this part over here basically is setting up the boundary conditions. These reaction diffusion equations are super flexible. So when whatever flow you're modeling reaches a boundary, you have multiple options, right? It can just keep going, it can bounce back, or it can just stop. So that's what we did. We said, well, when you reach a boundary, stop, because there's not a lot of forest in the ocean. So that was our logic behind that. I think that's pretty sound logic. But anyway, that was super, super fun. And these are the results. This is the model, and this is reality. And if you squint a little bit, you might see that they're pretty similar. They're not too different. I see Orlando squinting. That was funny. Orlando is a student in our lab, so he was like following directions. So, but yeah, you can see this, clear areas over here. You can see these areas of forest over here. So there's a lot of similarities that the model performed relatively well. But more importantly, it performed well with a very, very limited number of parameters. It was essentially 2 parameters. And the process of forest recovery, it's super complicated. It's super, super complicated. And we just model it with two parameters. But anyway, that was it. After the class, after collaborating with computer scientists, collaborating with mathematicians, I was hooked. This is it. I was finishing my master's here. Took me a little bit longer to do my master's. I did my master's in 4 years, but it was worth it. You know, I took a bunch of classes, a bunch of different things. I know a 4-year master's is not what Karen wants to hear, but you know, there was a different institution, different rules, but I was hooked. This is what I wanted to do. So I started to look for opportunities somewhere else that can give me more training in this interdisciplinary things, and that's where I found the University of Florida. That's when I came here to do my PhD. I applied to SNRE, and in those years, there was also an NSF IGERT, a program by NSF that would fund students to do interdisciplinary work. So it was pretty awesome. I had a lot of fun. So my dissertation had multiple chapters, and one of the chapters I wanted to do, you know, I talked with Orlando that, you know, you can have multiple chapters in your dissertation, and you can have multiple risks in each chapter, right? You should have some chapters that are pretty safe, you know, they're going to work. And if there's a chapter that, you know, you want to take some risks, that's fine. This is my risky chapter. So I wanted to sort of solve one of the oldest problems in conservation biology, meaning if you have a limited amount of resources to set up an area of protected sites, where do I put my money? Which sites do I select? And the way people have been doing that is by using different types of site selection tools and different objectives. One of the objectives is to select the sites that improves species representation. I'll select the sites that have the most species. At a single species, at the population level, you can select the sites that maximize species occupancy. But mainly, there's a little bit of interest not only on the patterns, but try to optimize those ecological processes like survival and movement. So that's the part that I was really interested. You know, I wanted to build a model that will optimize this in terms of survival and movement. But there's one interesting problem that nobody had really solved very well at this point, and it's the problem of uncertainty. Not so much uncertainty in the data, because uncertainty in the data, we know how to deal with that. You know, there's sensitivity analysis, information gap approaches that you can use. But this is about uncertainty in threats, right? So you set up your network of protected areas, but you don't know what's going to happen in the future. You don't know, which sites are going to get disturbed and which sites are not. So you cannot really predict if your system is going to be resilient or not in the future. So, it's really hard to predict the future. It's pretty hard to predict the future because the proximate causes that are, land use change and all that are rooted in super complex socioeconomic processes that are super difficult to predict. So how do people incorporate uncertainty today in these models? Well, the easiest way to do it is to select sites that are closer to each other, right? So if I have, these are all potential sites that I can select. I have a budget, I can only select 3. So I'll select these 3 because are the ones that are closer together. The rationale behind it is that if there's some sort of disturbance here, the animals can ideally disperse better to those sites that are closer together. But we got to be careful because by doing that, we're leaving out sites that are potentially bigger and better quality. So it's a solution, but it's not an ideal solution. So here's the problem. I wanted to build a quantitative application that will select a set of patches to protect or manage based on meaningful demographic processes like movement or mortality and survival that take into account uncertainty. And believe it or not, this is not an easy problem to solve. But I had already learned my lesson. When you have a difficult problem, you look for somebody that will solve it for you. So in this case, I went to look for help in the engineering department. And in the engineering department, again, I talked to a bunch of people. Most of them either didn't reply or say, I'm not interested, I make a lot of money, optimizing. I don't know what problems do they work on these days, but optimizing other stuff, they get millions of dollars, that they were not really interested in conservation, which is famous for not having a lot of resources. But when I contacted Dr. Cole Smith, he was like, huh, Miguel, that's a non-trivial, interesting problem. And we were in. And let me tell you something, this was another truly interdisciplinary interaction. I didn't know anything about engineering. I bought the book on network flow optimization, and I got until page 30. And that's it. That's as long as I got. And in Cole, his ecological knowledge was limited to a documentary he recently watched about bears. So you can imagine all our conversations being about how bears move through caves. It was a lot of fun. It was a lot of fun. But at some point, Cole in his infinite wisdom said, we're having fun. This is good, but you need to graduate in the next year or so. So let's bring somebody into the team. So he bring another one of the smartest people that I've met in my life, Jorge Acevedo, Colombian from Bogota. He was a PhD student in industrial and systems engineer, and we worked together on this problem. And by the way, so Jorge and I, after we finished, we went separate ways, and by chances of life, we're both back in UF. And we on the weekends we go bike, road bike riding and all that. So if you're interested in problems in engineering, actually Jorge can speak ecology. So go and talk to him. He's super nice, super efficient. Eats my math for breakfast, makes fun of my math. Super, super nice guy. But anyway, so we were in, and why working with engineers? Well, I was working with engineers because actually they solved this problem already. The problem that I wanted to solve was already solved, but it was solved in the realm of military applications. So imagine that you have a set of military bases, right? And there's some sort of flow that you want to maximize across your military bases. It could be the flow of ammunition, it could be the flow of medical supplies, it could be the flow of personnel, right? But you know that you have enemies, right? And the enemies wants to harm you. But you don't know what the enemies are going to harm you. So they say, if I have a little bit more money and I want to protect some of the sites, where do I put my money? And they did something super clever. And they said, well, I don't know where they're going to go, but I'm going to assume that my enemy is super smart and it has complete knowledge of my network and will harm my network in the places that it's going to harm it the most. And if I know that, I can build protective measures so that worst case scenario actually doesn't happen. Isn't that like super, super clever? And I was like, we can apply this to conservation. So in this case, we don't have, military bases, at least not in most cases, but we have, sites, forests or lakes or fisheries. Those are our discrete sites in space. And there's some sort of ecological flow that we want to optimize in that network. So we apply this idea of network flow interdiction, which has two parts. One, what I call the disturbance stage, which we identify what is the worst case scenario. What is the worst? What are the if I'm going to disturb a couple of patches, which one, if disturbed, are going to create the most problem for this network? And then there's the next stage, which is the protection stage, which is well, what do I do so that worst case scenario doesn't happen, right? And I haven't told you what are we optimizing in this case, but in this case, we're optimizing total individual life expectancy, or the amount of time that an individual remains alive and moving through the network, right? So what kind of data do we need for this? Sort of between patch probability of movement and patch survival, something that you can get from a multi-state model and capture mark recapture. We have, models to do that. And in this, we describe it as a reducible markup chain. And a reducible markup chain, an individual has three options. They can survive and stay on the same patch. They can survive and move to a different patch, or they can die and move to the death node, right? That sounds like Star Wars, right? The death node. But anyway, know that the probability of staying in the death node is 1, because once you're dead, you are dead. So there's no resurrection allowed in this model. But for most ecological applications, it actually works. So we build this network using total individual life expectancy and that reducible markup chain. And, the disturbance stage, basically what we're doing is decreasing habitat quality, right? So in this case, this animal, if nothing happens, it will live on average 20.43 years, right? So if I have a budget to disturb only 2 patches, this is the combination, patches 2 and 4, that it's going to decrease life expectancy the most. In other words, there's no other combination that is going to decrease this more than just these 2 patches. All right, so this is the worst case scenario, actually. If patches 2 and 4 get disturbed, this is the worst thing that can happen. That's the disturbance stage. So what do I do in the protection model? Well, in the protection model, I try to maximize what the disturbance model is trying to minimize, right? So I know this is my worst case scenario. If I protect one of these patches, already the worst case scenario doesn't happen, right? So I'm trying to maximize what the disturbance stage is trying to minimize. In other words, what this model is doing is saying, you know, disturbance, it's going to happen. Disturbance, it's unavoidable. It's going to happen. And I'm going to allow it to happen. But I'm going to allow it to happen in the sections of my network that is going to harm my ecological process the least. Isn't that cool? Like a little bit clever. But anyway, so we applied this to roseate terns and skipjack tuna in Southeast Asia. And we compare, you know, this is the baseline, you know, what you will get if nothing gets disturbed. This is the worst case scenario for both. And then we compare what you will get with our model versus what you will get if you minimize dispersal distance. And in both cases, actually following this network flow interdiction model resulted in higher total life expectancy than just minimizing dispersal distance. So that was pretty cool. And, you know, we're still working on some of that with collaboration with Rob Fletcher. We have continued work with this reducible Markov model. And we published a couple of papers. Andrew even built an R package to model connectivity using this reducible Markov chain approach. And today, you know, the adventure continues. Now, after that, I did a postdoc at LSU. I was faculty at the University of Puerto Rico for a couple of years. And now, so the way I say, you know, being faculty at the University of Puerto Rico was my dream job. So being here is like an inception, like an inception job, right? It's the dream within the dream. I will never imagine that I would be here, you know, having the professors that I admire and that train me so well, being my colleagues. But hey, I'm here. I'm enjoying every little bit of it. And I'm also enjoying working with some of the smartest students in the world. And I'm still working with interdisciplinary collaborations. Now I'm doing a little bit of disease stuff too. I'm super interested in vector-borne disease modeling. The students love this picture because they feel like the human is walking away from the mosquito. But anyway, so this is a model of vector-borne diseases. Here is the rate of change in the population of infected mosquitoes. This is the rate of change in the population of infected hosts. And you know, these models of vector-borne diseases have been applied to many instances of human diseases. They're super useful. We have learned a lot from them. But actually, they make some really interesting assumptions. They assume homogeneous mixing, meaning that every single individual has the same probability of being infected. And now we're all experts in diseases. We went through COVID, and we know that this assumption is not necessarily true, right? Some people are more likely to get infected than others. There's some people that went during the peak of the pandemic, kept going to Midtown and kept going to parties and all that, and they got infected really easily. Others kept their mask, kept their social distancing, and they were less likely to get infected. And I'm interested in understanding what happens when we violate this assumption. And, you know, some of the cool stuff is that some of the work that our students are doing in the lab are finding that actually heterogeneity happens in our system. So we know in the case of lizard malaria that those individuals that are bigger have a higher probability of being infected than those are smaller. So right from the bat, we're already violating the homogeneous mixing assumption. But there's also space that it's important there. So this is part of the thesis of John Michael Tui, who was a master's student in our lab, and he showed that sagray and sagray actually gets more infected in forested habitat than in deforested habitat. So we have size as a source of heterogeneity. We have habitat or space as a source of heterogeneity. So now I'm working with some of the folks here with Olivia Prosper and Nick Ruknananchai, developing models that incorporate some of this heterogeneity. And again, a bunch of ants on the screen. I'm not going to go through the equation, but what I just want you to see is that now, you know, when you compare the first equation With this one has subscripts, which means that now we have one equation for each one of the different patches or one for each one of the groups. And what we found, it's super cool, is that now when we start looking at these processes, things change. Our estimates of R naught, our estimates of prevalence are dramatically different when we start accounting for those heterogeneities. So that's some really cool stuff. One of the interesting things that I'm doing now is that I'm moving away from the spectrum, right? I'm still doing all the quantitative stuff, but now I'm starting to work with social scientists, which is kind of like a new thing for me. But something I learned in this process is that some of the lessons that I learned from working with quantitative scientists also apply when working with social scientists. Has to be win-win, has to be non-trivial, and has to be interesting problems. So now we're working with indigenous territory resilience in the Amazon in Ecuador, understanding those integrating, disintegrating forces, understanding how indigenous communities, if they're using the resources in a sustainable way or not. And we're working, this is an amazing team. I'm learning a lot from the social scientists, so the lessons still apply. I'm still working with Jorge. He's now here in UF, so we'll still sort of continue with this process. But now we're adding the human dimensions component into the modeling approach. We're working with Nia Morales to incorporate human perspectives, right? So when we design those network of protected areas, there's uncertainty in terms of disturbance from outside, but what about people's willingness to participate? What about people's perspectives? Those are super, super important, and that original work didn't include it. So now we're working with Nia to include that. So there's a couple of things, I don't know if you notice through my talk, and when we think about interdisciplinary ecology, we think about the merging of disciplines. I would like to argue this afternoon that it's not about the merging of disciplines. It's about the interaction of people. It's about the interaction of people of different disciplines. It's all about people, right? And as it turns out, I'm a big fan of the magic that happens when you have people in a room that don't speak the same language, the same academic language. That magic that happens when they start thinking from multiple perspectives, start thinking about the same problem and trying to solve it. And as it turns out, actually, I didn't make this up. Franz Johnson had this book and he called this the Medici Effect. That magic that happens when you put people in the room that don't speak the same language. And he argues that leaps in innovation happen at the intersection of ideas, disciplines, and cultures. And I cannot agree more with that idea. And I'm sure if you're here in SNRE, I'm probably preaching to the choir. And more importantly, this is a recent paper that was published in Nature showing that disruptive science is decreasing through time. And I like to argue that interdisciplinary ecology or the interdisciplinary sciences have the potential to bring this back. I think the disruptive science is going to happen by the interaction of the disciplines, not so much about doing the same thing the same way that we have done it in the past. Remember Paco from that picture? So when I was taking that class in mathematical biology, Paco came to me. By the way, we're really good friends, but he came to me and said, "Hey, Miguel, so what are you going to do for your final project in the class?" And, I'm going to use reaction diffusion equations. He looked at me and said, what's your math background? So I took Calc 1 like 5 years ago. And it's like, what? But, to do reaction diffusion equations, you have to have Calc 1, Calc 2, Calc 3, ordinary differential equations, advanced ordinary differential equations, and then partial differential equations. You cannot do that in a semester. You're crazy. When you're in an argument with somebody and it's after the argument is over that you think about exactly what you wanted to say. It took me 10 years, but actually I think I realized what I wanted to say in that argument. A couple of years back, I went to visit Puerto Rico on Christmas, and we were watching on TV a Philharmonic Orchestra doing a Christmas concert. And my mom asked me, "Hey, Miguel, do you think that the orchestra conductor knows how to play every single instrument in the orchestra?" And boom, I got my response to Paco. Of course not. Of course not. Orchestra conductors, they don't know how to play every single instrument in the orchestra, but they know how every single instrument sounds. And more importantly, they know how to integrate those sounds to make novel and better harmonies. The same way, we don't have to know how to solve every single ordinary differential equation in the books. That's what collaborations are for. But more importantly, we know the vocabulary, we know the models, and more importantly, we know how to integrate the models and the ecological concepts to create better novel knowledge. Thank you so much. Awesome. There's plenty of time for questions, and I hope to, create some discussions here. Do I have access to Zoomland questions?
You should, yeah, you should. There we go. There you go.
All right. So any questions from Zoomland or you're in the audience? Yes.
A little tangential, but why
Oh, that's a really good question, and I forgot the story, but I'll get back to you on it because he describes it in the book at the beginning, but I'll get back to you. Sorry, I forgot about it. Yes.
Okay, so you mentioned the article about the decrease in disruptive science, and what did the article say the reason was that, like, behind that?
Yeah, the reason is that we don't know. So it's interesting because its disruptive science has declined and no one knows why. And they haven't been able to point out a reason for it. And of course, if you look at Twitter or Mastodon or social media, everybody has their own favorite reason. From what funding agencies are funding, from what are people motives when we're doing science, risk aversion and willingness to take risks. Depending on your career stage, you might be willing to take more risks, less risks, and all that. Yeah. I do think that interdisciplinary ecology can bring us back. And I think we need more training like SNRE. And one of the things that I really like about SNRE is that it provides that safety net to take those risks. I mean, if you think about it, most of the stuff that I talked today, all these projects, they were pretty risky. I mean, there was a lot of potential for things to not work. But luckily, I had really good mentors. I was in institutions that were supportive, and they provided that safety net. You say, take the risk. If it works, great. If it doesn't work, we'll try something else. And I think that is going to allow us to do better science for sure. Other questions from Zoomland or here? Yeah.
You showed the map where you explained that forest cover was increasing in Puerto Rico. What are some of the reasons for that?
Yeah, so it's all political. It's all politics. So at the beginning of the 20th century, Puerto Rico was mostly an agricultural country, right? There was all the deforestation was mostly for sugarcane in the coasts and in the mountains for coffee and other agricultural products, also for charcoal. But then in the 1950s, so Puerto Rico had a U.S. military government until around the 50s. And then in the 50s, Puerto Rico had their own quote unquote self-government. And in that process, there was a lot of incentive for manufacture. So the people moved. We had this process of rural to urban migrate. By rural, it's a really tough word to pronounce in English, right? It's like rural murderer, right? I cannot pronounce it. But anyway, it was rural to urban migration. So people moved from the farms to the city to start working in other stuff. And those sites, they were abandoned, the forest took over, and now we have 60% forest cover. Now, that forest is different. It's not the same forest that we had before. It's dominated by invasive species and all that. But some argue that that's not too bad because eventually those invasive species are going to die, creating some sort of the scenario for the natives to come back. So anyway, if you're interested in forest recovery, I'd be more than happy to talk about it. And you can talk to Orlando too. He also worked with animals recovery and all that stuff. And also we're working with how animals respond to that forest recovery. We're finding some really cool results there too. Questions?
Hi, question from Zoom land out here.
Hey, Sarah.
Hi, Dr. Acevedo. So you know, you make a lot of good points why we should all be working interdisciplinarily, right? There's lots of great benefits, a lot of what you said. What's some of your advice? And you mentioned, you know, sort of both the problems and new things we can learn from when we're talking with people who don't speak the same academic language as us, right? Like when you get together with people from different fields. But it can also cause, you know, there's like gulfs of between understandings in different fields. What would be some of your advice for folks looking to sort of bridge some of those gaps?
Thank you for that question, Sarah. That's a really cool question. Of course, I don't have all the answers. But I can tell you some of the things that work for me and that work for other folks is that these are relationships, right? So sometimes we're gonna have relationships that are a good fit for us, the way we work and all that. Sometimes you're gonna try to work with people and we're not a good fit, and that's completely fine. But having the patience, right? You're not gonna write a science paper after the first meeting. And we need to understand that. We need to give some time and patience for this thing. These things develop, these things take time. So one of the cool things that we did in Puerto Rico is that we went to play beach volley, you know, and you know, we build these relationships inside the classroom, but we also build them outside the classroom. And those things, they take time, patience, and every relationship is different. So patience will be my advice now. But if I think of more, I'll write you an email.
Thank you.
Thank you. Any more questions, Sumlan? Here? I have like 4 minutes. All right. Yes, Shani.
I have one question related to the first thing that you published or you talk about how to about the program to classify or identify the amphibian species. And I was seeing in the table that the species with most false positive were Eleuterodactylus coqui. And I was wondering, like, if you guys took into account the heterogeneity of the microhabitats that they are around the island.
That's a really good question. So the reason for this, I mean, this is a relatively high, I think it's not super high, but it's a relatively high false positive. And there's 2 reasons for it. There's 2 species that call coqui. It's a 2. So right from the bat, you're going to have some confusion there between those 2. Do we took into account the heterogeneity? In a way, yes, because these recorders were everywhere in the island. So that heterogeneity will sort of be there. Do we consciously added it to the model? No, because these are machine learning models, right? So machine learning models, we can think of them as black boxes, right? They rearrange themselves in if you look at ChatGPT and look how many parameters, they have billions of parameters. I mean, not only millions, but they have billions of parameters in those models. So this is not something that you consciously, I'm going to add the habitat parameter here. Now those things rearrange themselves in the best way that they can find. So that was not a conscious effort. And the other reason why most of the things were confusing with coqui is that coqui was the most common species, right? So if you think about it, if you just want to guess, what's the sound? If I say coqui, I'm going to be right like maybe 60% of the time. So just by chance, it's better than winning the lottery. More questions? If not, my advice, keep doing what you're doing and do it well, because we really need you. Thank you so much. Yeah, I'll let you do this thing.
Okay.
I don't know.
All right. Thank you to everybody on Zoom. If you have any questions for me, let me know. Otherwise, I will see you next week.